All right, final exams are breathing down your neck. And let's be real, there's one topic that's a total nightmare for engineering students: fatigue. But hey, don't sweat it. For the next few minutes, think of this as your ultimate cram session. We're going to blitz through everything you absolutely have to know to crush that test. Ready? Let's do this.
Okay, here's our game plan. First, we're going to meet the villain of the story. Then, we'll become forensic investigators, learning how to read the crime scene of a fracture. After that, we'll see how we make materials talk under pressure, figure out how to map out the safe zones for our designs, identify fatigue's evil sidekicks, and finally, we'll nail down the must-know facts so you can walk into that exam with confidence.
All right, first up, let's meet the big bad of our story. And no, we're not talking about pulling an all-nighter. In the world of engineering, fatigue is this sneaky, silent killer that takes down mechanical parts when you least expect it.
I mean, who hasn't done this, right? You take a paper clip and you're not trying to yank it apart with all your might. No, you just bend it, back and forth, and then snap. It just gives up. Well, guess what? You just ran your very first fatigue test. And that simple idea, that repeated small action, is exactly what fatigue is all about.
And that right there is the textbook definition. You can think of fatigue as basically death by 1,000 cuts. It's not the one big huge hit that breaks the part. It's the buildup of damage from thousands, sometimes millions, of tiny little stress cycles, just like that paperclip, that finally, out of nowhere, leads to total failure.
And this is why your professors won't shut up about it. The original Spanish source nails it. Es una falla traidora. It's a treacherous failure. Why? Because it gives you zero warning signs. 1 minute, the part is doing its job just fine. The next, it's in 2 pieces. That unpredictability is what makes fatigue so dangerous and, such a big deal on your exam.
So, when a part finally gives up and breaks from fatigue, it actually leaves clues behind. The break itself tells a story. Our job as engineers is to be detectives and learn how to read that crime scene.
Okay, so every one of these fractures has a story, and it unfolds in a few stages. It always starts with one tiny little crack. Then, as the part keeps getting stressed, that crack grows, and the 2 sides of the crack rub against each other, making the surface look really smooth. Sometimes you'll even see these faint lines, kind of like ripples on a beach, they're called beach marks, showing where the crack paused. And then finally, the part gets so weak it can't hold on anymore, and you get the final, rough, sudden break.
Check this out. This is a broken elevator axle. See that part that's kind of smooth, almost polished? That's the fatigue zone, where the crack was creeping along for a long, long time. And that other part, the rough, grainy-looking section, that's the moment it all went wrong. The final, instantaneous snap. The whole story is right there on the surface.
And here we go again. Same exact story, but on an engine crankshaft. You see it, right? The classic signs are all there. The spot where the crack started, that telltale smooth zone from the slow growth, and then the rough area from the final failure. Seriously, if you see a picture like this on your exam, you'll know instantly that you're looking at fatigue.
Okay, so how in the world do we figure out how much of a beating a material can take before it just gives up? We can't just, guess. We've got to test it. It's time to put these materials in the interrogation room and make them confess.
And this gadget right here is our interrogation device. Basically, we take a little sample of a material, a specimen, and we stick it in this machine. It then spins and bends the specimen, putting it under a very specific amount of stress over and over and over. There's a counter just ticking away, 1 million cycles, 2 million, until, snap, it breaks. The machine tells us exactly how many cycles it took to fail at that stress level.
So we do this a bunch of times with identical specimens, but at different stress levels. Then we take all that data and plot it on a graph. And that graph, my friend, is the famous Wheeler curve, or, as you'll probably see it, the SN curve. It's literally the material's confession. The S is for stress, and the N is for the number of cycles. It tells us point blank, for this much stress, you get this many cycles before I break.
So the relationship is pretty simple, right? You hit the material with a really high stress, and yeah, it's not going to last long. It'll fail after just a few cycles. Drop the stress down a bit, and it survives for way, way longer. But for some materials, this is where it gets really cool.
See, for a lot of steels, that SN curve doesn't just keep going down. It actually flattens out and becomes horizontal. And what that means is, if you can keep the stress below that flat line, a level we call the fatigue limit, the material will basically last forever. It will never ever fail from fatigue. And a common rule of thumb for steel is that if a part can survive 10 million cycles, we just go ahead and say it has an infinite life. That's a huge deal in design.
Now that SN curve is awesome, but it's for a really simple, clean kind of stress. But let's be honest, the real world is way messier. We have complex loads. So for those tricky situations, we need a more advanced tool. Think of it as our safety map, and it's called the Goodman diagram.
Okay, to read this map, you just need to get two ideas. In the real world, a part is usually dealing with two kinds of stress at the same time. There's the average constant stress just setting on it. We call that the mean stress. Then, you have the stress that's bouncing up and down around that average. That's the alternating stress. The Goodman diagram is a genius way to look at both of those at once. Compare them to what the material can handle and figure out if your part is going to break.
What it boils down to is this. The diagram draws a line in the sand. It creates a safe operating zone. If the point that represents your combination of mean and alternating stress lands inside that zone, you're golden. Your part is safe. But if that point falls outside the line, failure is coming. It is the ultimate engineer's safety mac.
So, a material's fatigue strength isn't set in stone. It can be totally wrecked by a whole gang of bad guys that help fatigue do its dirty work even faster. Let's meet these notorious henchmen. All right, here's the lineup of fatigue's worst enemies. Things like sharp corners and holes are the biggest culprits. They're called stress concentrations. But also watch out for corrosion, high heat, even just a rough surface finish from scratches. All of these things are like an open invitation for a fatigue crack to start.
But if you're going to remember one of those, make it stress concentration. This is enemy number one. Just think of stress flowing through a part like water in a river. If the riverbank is smooth, the water flows nice and evenly. But if you put a sharp rock in the way, like a notch or a sharp corner, the water piles up and swirls around it with a ton of force. Stress does the exact same thing. It concentrates at that sharp corner, creating a massive weak spot. So the number one rule of designing against fatigue, get rid of sharp corners.
Okay, deep breath. We've gone through a ton of stuff really fast. So let's lock it all in. This is your final study sheet. This is the stuff you absolutely have to drill into your brain for the exam.
So after all this, you might be asking, why do we care so much? Why is this such a big topic? Well, because of this number, 90%. An estimated 90% of all mechanical failures are due to fatigue. Just let that sink in for a second. That's basically everything. If you get fatigue, you get why things break, period. All right, here it is, your cheat sheet. Let's burn this into your memory. Number 1, fatigue is failure from lots of small, repeated loads. Number 2, it's sneaky, no warning signs. Number 3, on a broken part, look for the smooth part and the rough part. That's your clue. Number 4, the Voller curve, or SN curve, tells you how long a part will last at a certain stress. Number 5, the Goodman diagram is your safety map for when loads get complicated. And number 6, and I want to say it again because it's that important, always watch out for stress concentrations. Sharp corners are the enemy. Okay, you've got this. You are ready for this exam. But remember, this isn't just about getting a good grade. This is about understanding the fundamental reason why things fail. So the real question, the one you should take with you long after the test is over, is this. Now that you know how things break, how are you going to go out there and design things that last forever?